Welcome back, mathematicians. Today we're on the last section of chapter 3, section 3.10, all about related rates. So now that we've gotten through how to take all these derivative rules, and I know chain rule, implicit differentiation, and all of this now, inverse trigs, I can now apply those to some problems. All right, so we're going to first be looking at problems that ask for the rate at which some variable changes when we know the rate of some other related variable or variables. All right, so we're first going to go through an example, and then we'll talk about a strategy to tackle these problems, and then we'll go through more examples using that strategy. Okay, so our first example is that the water runs into a conical tank, cone shaped, at the rate of 9 feet cubed per minute. When you see like feet cubed, probably means volume. Alrighty, the tank stands point down and has a height of 10 feet and the base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So always draw a picture. So that is a rectangle and not. What are these shapes? What? There we go. Okay. So we're going to do that and then make a cone. Beautiful. So here is our tank. She's beautiful and we love her. This is going to be our center right here, and then we're going to draw a line right here, and that's our radius. So that's what it means, base radius. It's like this guy right here, and he's 5 feet long, and then our height, so from here all the way down to here, is 10 feet. Okay? So as the water level rises, it's going to have another circle that's going to be the water level, right? So we can even make this blue for the water. Here we go. Beautiful. And that's also going to have a radius, and it's also going to have a height. Okay? So we're going to have kind of 3 things happening at once. We have V, which we're going to call the volume. And that's going to be in feet cubed. It's going to be the volume of water in the tank at time t. All right? We're also going to have our height of our water. We can call that whatever we want. Let's call it H. You can also think of it as the depth of the water in feet. In the tank at time t. All right? And then we're going to have the radius of the water as well, right? So if the radius is of the surface area of the water, because that's going to be a circle, right? So we'll call R, oopsies. Still in feet of the surface of the water. At time t. Okay? So there are a few things that we kind of need to pull out of our back pocket. The first one is the volume of a cone. And that is V equal to 1/3 pi r squared times h. I don't know how that comes about, but that's just the volume for a cone, okay? So then I need to get some type of relationship between r and h. So I know from geometry there's something called similar triangles. So there's this little angle here between the side of the tank and the center. If I stuck like a pole straight down the cylinder, that angle and the side would be the same angle for this blue triangle and for the big triangle, with one base being 10 and one being 5. So I have this little triangle, and then I have this bigger triangle. Oops, not H. That's 5 and 10. So this is like the big tank. So like the entire tank. And then this is R and this is H. So this is just the water section. These are both kind of like cross sections. So these are similar triangles. So that means the ratios are equal. And what we mean by that, so we're going to say, yeah. So using similar triangles, x divided by y equals 5 divided by 10. Make that a little clearer. This angle is the same, and this right angle is the same, so that means angles are the same, similar triangles by angle, angle, angle. Okay. So if I simplify 5/10, that's 1/2. And then I'm going to multiply each side by y, so I get that x equals what? 2, no. Y over 2, and by y over 2, x and y, I mean r and h, because those are the variables. Okay, coolio. Sorry about that. So I used this equation that I knew about similar triangles to get r and h in terms of each other. I did that because I have one too many variables going on. We can see here that volume, radius, and height are all functions of time, right? This is the volume at this time, the height at this time, the radius at this time. I need to somehow find a level, the level when the water is at 6 feet deep. So when the height of my water is the rate as that is growing with respect to time. I have one too many variables going on right now, okay? So I'm going to take my volume equation and I'm going to replace r with h over 2. So then h over 2 squared is going to give me h squared over 4. So that's pi, 3 times 4 is 12. H squared times h is h cubed. And that's our new equation for volume, all right? So now I want to find the level, how fast the water level is rising when the water is 6 feet deep. So we want the change in height with respect to time. when h equals 6, and what else am I given? This is the rate that my volume is changing, right? My volume of water. So h is going to equal 6, and dv dt equals 9 feet cubed per minute. Alrighty? So I'm going to take my volume equation, v equal to pi over 12, h cubed, and I'm going to take the derivative with respect to t. I'm going to move this over a little bit. Okay, cool. Act like there's a d dt right there. Okay? Well, how do I find dv dt? H has a t, like how do I do this? Remember kind of what we talked about with implicit differentiation and chain rule? I know that dv dt is going to be the same as dv dh times dh dt. Alrighty? So I'm going to take the derivative of v with respect to h and then multiply that by dh dt. So that's going to be pi over 12 times 3h squared times dh dt. Alrighty? Now, so dv dt equals 3 over 12, that's just pi over 4, h squared 6, and I don't know what dh dt is, I'm trying to figure that out. Remember we're given dv dt, that equals 9. So I plug that in, so I get 36 pi over 4 times dh dt. That's all equal to 9. And I'm trying to solve for dh dt, so I'm going to multiply each side by 4 over 36 pi. Four times 9 is 36. And we get 1 over pi dh dt. So let me check my units. So how fast is the water level rising when the water is 6 feet deep? Water level is rising 1 over pi feet per second, minute. And that's our final answer. All right. So now let's talk about strategy that we kind of already did. So for related rate problems, we're going to first start by drawing a picture and naming the variables, right? So I named it R and H. I also named some constants like my outer cylinder's height and my outer cylinder's, cone's radius. Those were 5 and 10. I could have also named those something else because they're constants. I could have been like radius, R sub c, H sub c, something like that. And we're going to also assume that all the variables that we're going to talk about, that if they're not constant, they're differentiable functions with respect to time. Okay? So step 2, we're going to write down any numerical information. So we wrote that we knew that H was 6, and we knew that dV dt, the change in volume with respect to time, was 9. That's numerical information, okay? And then we wrote down what we were asked to find, right? We wrote down that we needed to find dH dt, right? That is the change in height or depth. Same thing, kind of what we were talking about, was with respect to time. So we then wrote an equation that related the variables. I had 3 variables. I had radius, I had height, and I had volume. So we might have to combine 2 equations, right? So I had like a relationship between R and H, and I also had an equation with volume R and H. So I had to combine them. And then we differentiated with respect to T, and we evaluated. We plugged in what we knew to find the unknown rate. All right? So now that we're going to try that again with another problem and see how that works for us. Alrighty? So now we're given that a hot air balloon rising straight up from a level field is tracked by a rangefinder, kind of like if you've ever seen like a surveyor with those like little things that look like he's taking a picture. And it's 150 meters from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at the moment? So, step 1, we're going to draw a picture. So I have a balloon going up into the air. So we're going to call this my balloon. This is my rangefinder right here. This is my angle. Call it theta. That's a 90-degree angle. I know that this distance from the rangefinder to the liftoff point, that's a liftoff point, that's going to be 150 meters. And let's call this h for the height. Alrighty? So I think we named everything we needed to. So next, now we're going to write down some numerical information. So something that we couldn't really fit in our picture. We're given that the angle is increasing at 0.14 radians per minute when the angle is pi over 4. So I called theta my angle, so d theta dt, the rate at which the angle is changing with respect to time, is going to be 0.14 radians per minute when theta equals pi over 4. All right. So step 3 is to write down what you are asked to find. So we're asked how fast is the balloon rising at the moment. So that's going to be the change in height with respect to time. So we want dh dt. Okay? Next, we are going to write an equation that relates the variables. So I have an angle and I have 2 sides. One's constant, one's moving. So from what I know from trig is that tangent of theta equals opposite over adjacent. In our case, we are opposite to the height and adjacent to the field, which is 150 meters. So I get tan theta equals h over 150, and then I can rewrite that as like 150 tan theta equal to h. Same thing, just kind of writing it. I hate writing fractions. All right, cool. So thankfully I was only given 2 variables here, an angle and a height. So I want to find dh dt, and I have h equals this equation. So let's take the derivative. Right, that's step 5 anyways, differentiate with respect to t. So I'm going to have d dt of h equal to d dt of 150 tangent of theta. And we're assuming that theta is differentiable with respect to t. So I'm going to have dh dt equal to 150. Tangent's derivative is secant squared theta. Theta's our inside function, so we took the derivative of the outside function, tangent, with the inside still the same, theta, times the derivative of the inside, which is d theta dt. Perfect. So now we need to evaluate. Well, we're given that this is at when theta equals pi over 4. And that's also when d theta dt equals what? 0.14. So I'm only left with an unknown of dh dt, and that's what I want to find. Perfect. So then what are we going to do? So I have dh dt equal to 150 secant squared of pi over 4 times 0.14. Secant of pi over 4 is the square root of 2, so this is going to be 150 square root of 2 squared times 0.14, and multiply that all together, and we get 42. But I need some units on this because I was given units in my problem. So if we were given that the radians were changing in radians per minute, and that this is in meters, so my height is going to be changing in meters per minute. Alrighty, and we're done. Okay, so take a second to review that. That went a little fast. I kind of have everything written already, so this might be a faster lecture than you might have been prepared for. All right, so next problem is, this is like why I wrote all these problems ever. You have to like sit here for like 15 minutes as I wrote this out. So we're given that a police cruiser is approaching a right-angled intersection, right? Like a four-way intersection from the north, and is chasing a speeding car that has turned the corner and moving straight east. When the cruiser is 0.6 miles from the intersection, the car is 0.8 miles to the east, and the police determined with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour, what is at that instant that they measured them to be moving 20 miles per hour away? What is the speed of the car? So this picture is going to be a little bit more detailed. So here is our road. And we have Mr. Policeman right here. And this other car, let's make him green, over here. Alrighty. So this is our picture that we're gonna use, right, just to kind of visualize what's happening. The red car is going down, and the green car is going out this way. Okay? We can also kind of redraw it and do something a little abstract. So this point is the intersection. Call that INT. This is going to be the car, that green car, and this is going to be the cruiser at this point. All right? So let's call this point like ground zero, the intersection, right? And then, so that means the intersection of the car at one point is going to be 0.8, while the other one is going to be 0.6. So let's call this x and this y, and the distance between them, let's call it just d. Alrighty? We're assuming that x, y, and d are all differentiable with respect to t. So that means there's a dx, dt, dy, dt, maybe not dd, dt. Let's make that z. Okay. So we drew a picture. Great. I know at some time t that y is 0.06, x is 0.8, and the cruiser is moving at 60 miles per hour. So dy dt. So notice that the red circle, the cruiser, is going towards the intersection. So the distance between the intersection and the cruiser is decreasing. And that means that this is going to be negative 60 miles per hour. Right, so it's getting closer. So even though I'm going 60 miles per hour, it's going to be, the distance is getting smaller. So that's why it's in negative miles per hour, okay? If I'm going towards something, the distance is getting smaller, so it's a negative, okay? And we also know that dz dt is 20 miles per hour because it's increasing. Ready? So we don't have any angles here, so we're not going to use any trig functions. So we are going to use the Pythagorean theorem. Identity. So that says that x squared plus y squared equals z squared. You guys have also seen this as a squared plus b squared equals c squared. Same thing. That is our related equation that we're going to use, okay? So, what are we trying to find? Hold on. We want to know how fast the car is speeding. So we want to change in x, so d dt. All right? I kind of switched 3 and 4. So now we're going to differentiate with respect to t. So we were going to take dt of x squared plus y squared and the derivative of z squared. So we already made the assumption that x, y, and z were differentiable with respect to t. All right, so now this kind of looks like implicit differentiation, except everything's with respect to t. So that means that when I take the derivative of x squared, it's going to be 2x dx dt plus 2y dy dt equal to 2z d dz dt. Alrighty? Every term has a 2 in it, so I actually can cancel out these 2's. If I divided by 2, it would have been the same thing. So now I'm left with x dx dt plus y dy dt equals z dz dt. Okay, cool. So let's plug in what I know. I know x and y. So I know that x equals 0.8. I don't know what dx dt is. I'm trying to figure that out. So I'm just going to leave that as dx dt plus y is 0.6 at this instant. And then dy dt is negative 60. I was never given z, but I think we can find it. So let's just hold z right there. And dz dt we were told is 20 miles per hour. So now let's find z real quick. Remember how we knew that x squared plus y squared equals z squared? Well, let's plug in that because I think that'll give us what we need. So that's going to be what is x? X is 8. Squared plus 0.6 squared equals z squared. I actually haven't found out that number yet. Oh, look at that. So we get 0.64 plus 0.36 equals z squared. Well, that just equals 1. The square root of 1 is z. Pretty cute. Okay. So now we have 0.8 dx dt, that's what we're trying to find, plus 0.6 times negative 60, so that's going to be minus 36 equal to 1 times 20, which is just 20. All right, so now I'm going to add 36 to both sides. So I get 0.8 times dx dt equals 56. And then divide everything by 0.8. And that equals exactly 70. And I need to check my units. These guys were all miles per hour. So this is miles per hour. And boom, he was speeding. You guys should try to use this if you're ever in this situation and the cop tells you you're speeding. Go math on him and let me know if it works. Okay, cool. So a lot of these problems do have triangles. That's usually the main one. So we're gonna do one more problem that does have has like kind of the triangle as its picture. And then I'm gonna give you guys some of the area and like the surface area equations that you should like know other than like a rectangle and a triangle and trapezoid. I expect you guys know all those. So we're gonna do one more problem and then we're gonna be done with this section for the day and done with chapter 3. Alrighty? So this next problem I really like because it kind of shows all the different questions that you can ask just given one problem and one little picture. Okay, cool. So a 13-foot ladder is leaning against a house when the base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. So before I even read part A, I'm going to draw my masterpiece. Okay, so there's our ladder. And so this is going to be the wall. And, oh wait, not the wall. Yes, wall. Okay, cool. And I think that's it. Ladder and the base. When it means base of the ladder, it means that base of the ladder. Okay, cool. So as the ladder is falling down here, this base is gonna go out that way. Okay? So the first part of this question asks, how fast is the top of the ladder sliding down the wall? Then being at when the base is 12 feet from the house and moving at a rate of 5 feet per second. So what I like to do for these questions, because it sometimes gets a little crowded, is I like to draw kind of a snapshot picture of like, I know that at this specific time, the ladder's always 13 feet, the base is 12 feet, and then I want to draw the rates. So on this beautiful picture, we're gonna call this ladder is 13. The base, let's make it blue. It's 12. And I don't know that distance right then quite yet. And then I'm gonna have a second triangle. This is gonna be a rate triangle. Rate, okay? So the ladder actually changes never. The ladder is just gonna stay. So its rate is 0. And the base is changing. The base is moving at a rate of 5 feet per second. So this one is 5, okay? So that angle is gonna be the same as this angle. Everything's cute and happy. So we're gonna use the same equation that we used last problem, Pythagorean's identity. So that says that the distance of the wall squared plus base squared equals the ladder squared, okay? You can choose whatever letters you want. You can choose like shapes. You can choose smiley faces or frowning faces, emojis, like whatever. They don't have to be W, B, and L. Sometimes I also do this with like A, B, and C, but I already called it wall, base, and ladder. You know, I want to know if someone's like named their kid Ladder. I'm gonna look it up. Okay. Water break. So I don't know my wall, but I do my base. It is 12. And this is 13. This is L squared. This is actually, I forget what these types of triangles are called, but it's like, they're like perfect numbers. And so, what is this, 144 and 169. And if I subtract them, I get that W squared equals 25, and that W equals 5. Beautiful, and I've completed this triangle. I still don't know what this is. Oh, not 0. But I want to find him. All right, so we want, what is that word? We want dW dt. Alrighty? So I have a picture. I have what I want. I found an equation for them. And I've kind of, in these pictures, drawn what everything is. So if you don't like to write out like kind of like dB dt equals this, dL dt equals that. That's kind of why I like a rate triangle or like a separate picture, and I can relate them back to each other. Okay, cool. So we're gonna take our handy dandy equation and differentiate with respect to t. So So we'll get that. And then similar to before, we know how to take what this derivative is going to be. It's going to be 2w. Instead of w, dw, dt, and all that, I'm just going to write w prime plus 2b, b prime equal 2l, whoa, cray cray, l, and l prime. You don't have to. It's just what I want to do. Okay? So looking over at my pictures, I know that I'm going to have 2, what's w? 5. W prime is, oh, my boyfriend's calling me. Sorry, bye. What's W prime? Oh, I don't know. Plus 2 times, what's B? 12. And that is changing at 5. And this is going to be 2 times 13 times 0. Alrighty? Ooh, I just realized something. Just kidding. I didn't realize anything. We're fine. Okay, cool. So this, I didn't take care of the 2's, whatever. This is going to be 10 W prime plus 12 times 5 is 60 times 2 is 120. And that is equal to anything times 0 is 0. So 10 W prime minus 120 and W prime equals minus 12 feet per second. Does it make sense that it's 0? Oh, not 0, negative? Yeah, it actually does. Since the distance between this wall, it's going down. The distance between the top of the ladder and the ground is shortening. It's decreasing, so it does make sense. All right, perfect. So then let's do, we're gonna skip part C because it has to do with the area of the triangle, and I kind of feel like giving that for you guys for homework. So I'll put that. All right, so C says, at what rate is the angle between the ladder and the ground changing? I'm gonna give you guys a few seconds to think about that, and then we'll wrap it up, all right? Okay, so I hope you guys tried that one. So let's walk through it together. So remember, we're doing at what rate is the angle between the ladder and the ground changing? So if we scroll up, we see we have that original picture with the ladder and the base and the wall. Let's redraw that with some angles. So we have the wall, the base, and the ladder. All right, we have the angle, which in the textbook, it's kind of more explicit of which angle it's talking about, but it's talking about theta right down here. So that's gonna be 90 degrees angle. And we can kind of draw a rate triangle again. Wanted to where we have like theta prime, which we don't know, we're trying to find, right? So there's lots of different thetas that we can use, right? Let's choose one where one side isn't moving. So we know the ladder isn't moving. We called L prime. And what was L prime? We figured out what it was, right? Oh, it's 0, right? It's because the ladder's not moving. And we know the wall is 5 feet at that point, and we know that it is decreasing 12 feet per second, right? So what trig function can we use that does opposite over hypotenuse? Right, sine theta. If you remember SOHCAHTOA, I use it all the time. So in our case, the opposite we call W, and the hypotenuse is L. I like to use L here because L is kind of like a constant. It's not moving. We don't have to do quotient rule at all. Thank God. Right? So we have our equation now. If we wanted to, we can even kind of multiply L over, and so we'll get L sine theta equal to W. We don't have to use sine. We could have also used cosine. I think we also could have done tangent. Just different ways. They're all the same. Just gives you a little different relationship between the sides. So we're going to take the derivative of each side with respect to t. And remember, L is a constant here. So it's just going to say that it's going to be like L, not sine theta, cosine theta times theta prime, or d theta dt. Let's write that. Alrighty, and that is going to equal W prime. So we can just like plug and chug right now. So I know that L is 13. I know that cosine of theta is equal to something later. We'll figure that in a second. Times theta prime, which is what we're trying to find out, equal to W prime, which we just found out is negative 12. So then cosine, so we have sine theta is opposite over adjacent. Remember that cosine theta is adjacent over hypotenuse. So adjacent is going to be the base, which we were told is 12. Hypotenuse is 13. So we get that. So we'll have 13 times 12 over 13 times theta prime equals negative 12. Oh, that's a 13. So then 13 over 13 is going to cancel out. And we're left with 12 theta prime equal to negative 12. Well, divide each side by 12. And we get that theta prime is negative 1. And we're going to make that radians per second. Yeah, because our time is counted in seconds, not minutes. Alrighty. So that's how we could easily have a whole different type of problem with the same maneuver just by asking a different question. All right. So there are a lot of different area and volume and surface area equations that are used, but there's kind of some ones I want you to know. So I'm not going to write all these equations out, but you should know how to find the area of a square, triangle, trapezoid, and a circle. And then same for perimeters. And then, Winston. Surface areas. So the surface areas for a 3D object. And if you know the surface area, I also want you to know volume. So that is a right cylinder, right cone, a sphere, a cube, and a pyramid with a square bottom. Alrighty? So these will come up later. The more we learn about how we can apply derivatives, but these are usually just the ones that are really good to know, especially cone and cylinder. Did I spell cylinder right? Nope. Alrighty, so that is it for related rates. If you're still a little struggling, I suggest going through this again or emailing Bailey or I and watching Bailey's video for this, and he'll go into more problems. Alrighty, see you guys later.